Perfect. Let's get started. So, hi everyone, welcome to each and every one of you. We are super excited to have you join us for today's session, which is going to be on search that thinks how RAG and ESRE can elevate GenAI experiences. Today's live session is going to be super insightful, a lot of fun, and to everyone joining us today, a very warm welcome from the full Hyperflex team. I am Jessica, and I am your user success manager at Hyperflex. Hyperflex is an Elastic certified partner, and it is built by passionate elasticians and Elastic certified engineers. We have a team of over 20 Elastic certified engineers, and we work across sectors and across the globe. We're dedicated to being and helping companies get the best and absolute most out of their Elastic stack, whether it's search, observability, or security. We work across sectors, as I mentioned, helping teams design their Elastic solutions that are not only powerful, but also cost effective, scalable, and built to last. We offer Elastic consulting, and we also offer other services like managed services, migration services, implementation. So, as I said, whether you're just starting off with Elastic or you're really deep into the GenAI use, we're here to help you build every step of the way. And today's session is all about RAG and Elasticsearch Relevance Engine and how that can unlock new dimension of experiences and intelligent search for all your GenAI apps. And today I am joined by two of our brilliant speakers, Naman and Vishwajit. Naman is an Elastic certified engineer and Vishwajit is a senior software developer. They'll be walking you through the full hands on experience today. They're going to cover everything from the fundamentals to real world implementation. Before we get started, I'll hand it over to our speakers to introduce themselves. And Naman and Vishwajit, I would love if you could share maybe one fun fact about yourself. And a quick note to everybody else joining us on this call, feel free to drop your questions in the chat box at any time. We have a designated Q&A session right at the end where we will be taking up all your questions that you asked during the session. So, all right, over to you, Vishwajit and Naman. I would love to learn a little bit more about you. So, introduce yourself and a quick fun fact.
All right. I will start in mine. Hello everyone. Thank you everyone for joining. I am Naman Agrawal. I am a senior Elasticsearch engineer at Hyperflex. I am Elastic certified engineer and a certified Kubernetes administrator. I have been working with Elasticsearch search and observability use case for quite a few long time. And my fun fact about me would be that I'm a football nerd and a Barcelona fan. So Forza Barca.
And Vishwajit, we'd love to learn something about you as well.
Um, Hi everyone. Talking about a fun fact. I recently was working on a project which was real-time speaker diarization, and then I thought that I had that eureka moment where I had created something very similar to Super Whisper. That company got funding around 5 million. So actually, I thought that I had created something very similar to that. But then later on, when I got to see the logs, that was not the case. Um, this was a fun fact. And talking about myself, I'm Viswajit. Uh, I really like working on backend side along with GenAI. And yes, I'm currently working as a software developer in Consultad. Uh, okay, so let me just walk you through what sort of things we'd be doing today. I'd be starting with a very basic scenario of how LLM works, a very basic idea, and then I would go into how RAG works and what are its components. So RAG seems pretty, a very fancy word, right? So we'll try to dissect it and understand it in a very simple uh, manner. So let me start with sharing my screen. Uh, okay. So talking about LLMs, which are large language models, uh, LLMs are trained on a very vast amount of internet data, right? So what actually happens is that as it is being trained on all the internet data, so it needs to hold the data as well, right? So it actually holds the data in its parametric knowledge, which we call it as weights. And to be able to access the data, we use prompting. So we use prompt, we give it to LLM, and then LLM serves the knowledge in its parametric knowledge store, in its weights. And then with the help of sequence generation of text, it gives us a response, right? So because LLMs are being trained on all the open source internet data, right? It actually lacks where you want to ask a question which is very, private to your specific domain, for which the LLM has no context about. So, for example, if you ask a question on about your company specific data, it will not able to answer because that LLM haven't seen that answer, right? Second kind of thing is that if you ask the LLM about a very recent event, so it won't be able to give that answer. The reason being that there is a cutoff date, right? So let's say till January 2025, a model has been trained, right? So it can give answers only to that particular point of time, not the answer till now, right? But you can ask that ChatGPT still gives us answer of latest information if we ask. So this actually happens because ChatGPT has the tool calling functionality. So it can call Google search and then it can get the result and then it incorporate and it and then uh, give us the updated information, right? But if you go to Hugging Face and then download a model and then ask something about a recent event, it will not be able to answer, right? So yeah, this is the limitations of LLMs, and this is where RAGs comes into the picture. RAG is retrieval augmented generation. So this is a very simple flow, right? Where we give a query, which is actually a prompt only, and then we give a context of, okay, this is a context, and then this is a question. You give it and you make it a prompt, right? And then you give this prompt to LLM, and then the LLM generates the response, right? So this prompting step is also called as augmentation step. Augmentation is just a fancy name of making the prompt, right? Now, where we would be getting context, right? We can give context manually, but not every time it's possible, right? That we are giving, the LLM the context every time because it will be very hard for us. So we try to automate this process, right? And this complete process is called as RAG. So RAG has four things. First one is indexing, which is actually collecting the data and then uh, putting it into a vector store where we try to put the data into a vector store so that LLM can infer that particular data and then it can take the context and then generate the response, right? So for example, if it's about a very specific domain of medical, what we will try to do is that we'll try to extract the proprietary medical data and then we'll try to put it in a vector store. A retrieval step is when it takes our query, it generates an embedding of the query, and then it tries to query the vector store. And after querying the vector store, it actually gets the context. So yeah, this is the retrieval step, which is retrieving the context from the vector store. And augmentation step, where we now get the context, we already have a query which the user has asked, right? So with this help of query and the context, we'll be doing this augmentation step, which is just making a prompt. And generation step, where we give this prompt to LLM to generate a response. So yeah, this is the actual flow of RAG. So yeah, RAG is nothing but query and context combined. Now, this is the four major component of RAG. So we have first document loader, where we try to take the document and load it into a vector store, right? Or we load it in memory, and then we can have a text splitting, right? Where we can try to split uh, the the large text or the large corpus that we have taken. So for example, in the current demo, we would be trying to take or use a text from 2 hour podcast. And then we can use document loader from LangChain, or we can use, just a string combination. And then we'll try to do a text splitting. Text splitting is really necessary because we want to chunk the data as well, right? We cannot give the complete context. So let me tell you why this text splitting is important. Reason being that imagine you have a PDF document that has 30,000 pages, right? Now, LLM have a context limit that is 4,000 to 32,000, right? So if you have 30,000 pages in a PDF, you won't be able to give it to LLM, right? Because it will go out of context. And then, getting the correct context from this long PDF is very hard for the LLM, right? So it's again a challenge. That's why we tend to do text splitting. So what we can do is that we can actually split based on the pages. So for page number 1, we can put it in a different chunk for page number 2, and then so on. A vector store is just for doing a semantic search. Why? Because it does a similarity search and get the context. And then we have retrievers. Retriever is just prompt combined with LLM, and then actually retriever is just query with embedding, and then you'd be getting the context. That's it. Okay, so I'd be explaining you what sort of demo I'll be doing, so that RAG concept will much more be clear in this context. So yeah, today we'll be doing this particular thing where we'll be having a YouTube video link. We can use ID for that as well. And then what we'll be doing is that we'll be trying to get this YouTube video in form of a string. So this string can be considered as document. And then we'll be trying to chunk that document. For reference, we'll be using a 2 hour long YouTube video. So it will be a quite long transcription. And then we'll try to chunk it. For simplicity, I'll be chunking just on 1,000 words. And then I'll try to use an embedding model offered by OpenAI. And then I'll try to form chunks. And then after forming chunks, I'll be putting it into a vector database. Which one? I'll be using Facebook AI Similarity Search Vector DB. Reason being that it's very easy to spin up. But on production, you can use something like Elastic, you can use Pinecone or Quadrant, right? Which are much more production ready. And then what we would be doing is that when you would be passing a query, it will be going to the retriever step. And then with the help of that retriever, it will do a semantic search on the vector database. And then it will be giving out and taking the context that, okay, this query matches which chunk. We can actually try to get top 4 or top 5 chunk so that we'd not be missing up on other things as well. And then after getting the context, we'd be having a query. So a query is already there, right? So we can combine the context and the query, and then we'd be getting a prompt. We're deforming this prompt and giving it to LLM so that it can generate the response. I'll be doing everything, every step over here in a separate manner. So yeah, collab will be helpful. So yeah, I'd be showing it in an individual component. And then we can see that how exactly it is generating answer, seeing the context. So you would be able to see the chunks, you would be able to see the vector database, what exactly it contains, and then you'd be able to see what context it has. And then after augmentation step, how exactly it looks like. And then we'd be trying to form this response. If everything is, if everyone is good with this, I can start with the demo. So yeah, please give me an acknowledgement. So my screen is visible, right? I'll be starting with the very first step, which is we'd be trying to go to the, we'd be having a YouTube video ID, and then we'd be going to that video link. We'd be trying to get the transcription, okay? So actually, to make things handy, I have already pasted, have the code ready, so I'll be pasting it. And then we can see these things in real time. So yeah, this is the indexing step. And then when I'm running this, then what we are doing is that we are having everything in this transcription. So we have printed this transcription, and this is a very long transcription of 2-hour video. So this transcription list, it actually contains something like this. So yeah, it has a text, start time and end time. So we have just conjuncted every text, into a form of continuous string. So after this indexing step, we have this particular step where, we try to, do text splitting that I talked about, right? So we'd be splitting the text based on, let's say, 1,000 words. So we'd be having a chunk of 1,000 words, and then we'd be needing some overlap as well, because it would not, miss on the context, right? So yeah, for the text splitting, I'd be having this text splitter, and then we can simply check the chunks length. So we have 168 chunks, right? So this thing that I talked about. So we have this 168, this chunk. And then after this one, also we can actually check what this chunks contain. So let's say chunk of 100. And then this contains something like this, right? Which is a part of that particular transcription. Now what we'd be doing is that we can try to generate the vector embedding, and then we'd be using a vector database. So the vector database I'd be using is Facebook AI similarity search. And then the embedding, I'd be simply using an OpenAI embedding for this one. Okay, so we have the embedding, we have the vector store, and also we can peek into this vector store as well. So let me just try to show you how exactly things looks like in this vector store. So we have this ID and we have this hashes, or you can say indexes as well, where let me just scroll it down. So yeah, this is how it actually looks like. To be able to see the exact content that is present in this chunk, we can actually try to use this function called get by ID. So let me just try to use this function, and then I can use this hash, and we would be able to retrieve what is present in this in this particular hash ID. So yeah, this is the ID of this one, and then this is the page content that we are having. Now, what we can do is that we can try with this particular thing, right? We need a retriever, and the retriever that we will be using is from the vector store that we have created with the help of the Facebook AI similarity search. So let me create a retriever. So yeah, we have this retriever, and then if you try to print this retriever, this is just a vector store retriever, which is based on Facebook AI similarity search. And then we can simply now ask a query and then see what sort of chunk it is going onto the vector database, and then it is trying to get us back. So let's say, we asked that what is DeepMind. I have already seen this video. So yeah, so if we ask this, so we had used k equals to 4, right? So it is giving us 4 very similar chunks that is found in this vector database. So yeah, this is the first one, this is the second one, and this is the third one. Along with this is the fourth one. Also, to give it a context, right? This is actually in the key value pair and in a document form, in list form, right? So what we can do is that we can try to convert it into into a continuous form of string. But yeah, we'll do it a bit later. But yeah, let's come into the augmentation step, where we will be using a LLM, and then we'll be forming the prompt. So this is the augmentation step. I'm just using this model 40 mini. Why? Because it's cheap. And then this is the prompt that I'm using. So yeah, this prompt is a very basic thing, that it is a helpful assistant, and this if the context is insufficient, this should see that it doesn't know. Also, I'll be trying to form a question, and then we can see that for that particular question, what exactly it is retrieving. So yeah, the same thing we'd be doing this here. So yeah, if you print this retrieve doc, it will again print the 4 similar thing that it has got from the vector store. Now what we can do is that now this is scattered, right? So we can convert it into a common string. So yeah, I'm just using a join function. So now this is the combined string, right? Earlier it was a 4 different document ID. And then let's try to see how the final prompt looks like. So we are having a context, we are having the question, and then we'd be forming the final prompt, which is actually the augmentation step. If we try to look at this one, this is how the final prompts look like, that you are a helpful assistant. And yeah, so with this, and this is the context that we have given to this one. And then to be able to generate the answer, we can just use the LLM object that we have created, and then we can invoke it with the final prompt that we are having. So yes, because this is not in the form of answer, right? This is the chunk that it has got, and now this is how the answer is coming. That the topic of, the question was, is nuclear fusion discussed in this video? And yes, this is the answer. That okay, it was discussed, and yeah, these are the things that were discussed. So yeah, that's all about the demo. But this is a very complicated process, right? We had different steps and all. So I'd hand it over to Aman so that we can see a much more simplified way of doing the same thing. Over to you, Aman.
All right. Thank you so much, Vishwadit, for a great demo on how, what, and why RAG is there. And so I would just like to know from you guys, how many of you have actually used RAG before? Also, do you think it's a bit complex? Uh, you can share your views in the chat, guys. To me, RAG seems a bit complicated, right? But it's incredibly fascinating, right? Now imagine this. What if a developer had a low code interface that lets them to use these LLMs of their choice with their own data just in minutes? Something intuitive, some hands-on, and honestly fun to use, right? Well, here comes the Elastic Playground. Elastic Playground is a low-code interface that empowers developers to quickly prototype RAG workflows, experiment with hybrid search, semantic re-ranking, and connect LLMs without having to write complex backend code. So you might be wondering why this even important, right? When you are prototyping a conversational search, the ability to rapidly iterate over components like retrieval method, keyword, either vector or hybrid, or re-ranking strategies, it is crucial for reducing hallucination and improving answer quality. And that's exactly what Elastic Playground, powered by Elastic Vector Database and Search AI platform, lets you do. You can do A/B testing with different LLMs like OpenAI, Anthropic, etc. Plug in private data via elastic indices, refine retrieval methods using BM25, semantic search, or hybrid. Use elastic transformer modules or open inference APIs to do so. So enough of talking. Let's actually walk through to build a RAG application using the Elastic Playground. Okay, so Playground is accessible within Kibana using the Elasticsearch UI. Just head over to the sidebar and go to the Playground. Okay, here it is. Okay, so Playground is a very good UI for us, a low code interface where developers can work and learn more about LLM and redefine their RAG application. Firstly, Playground supports chat completion models using ChatGPT 4.0 from OpenAI, Azure OpenAI, and Anthropic via Amazon Bedrock. To begin, we have to connect to any of this provider and bring LLMs of your choice. In this demo, I have already configured an OpenAI connector. You can see over here, I have already connected a demo OpenAI connector with a type of OpenAI, and we can test this as well. All right. It's runs all right. So we are good with that. Uh, you can chat with your data, even indices based on BM25, that is full text based searching. You can also have an option to use text embedding models, Elastic Zero Sort semantic search model, that is ELSER, though it's not mandatory. You can always go with full text based searching and use BM25. Getting started is really easy. Just select an indices you want to use to ground your answers, and also just start asking question. Right. Let's just quickly ask you question. How are you? All right. So you can see that we do not have any indices being selected. So firstly, we'll select an indice. Now ask, how are you? Okay. So you can see that it got a response from the OpenAI 4.0 model, that is, I'm just a computer program, I don't have feelings and so on, right? So in this demo, we are going to use a PDF. We'll index this to a BM25 index. Each document represent a page of the PDF. Let's go through the PDF. It's a normal layout parser PDF with 16 pages. so much of reading, right? Let's not do that and just use this PDF to give context to our RAG application, right? So first, we'll install all the dependency and use something called PyPDF to read this PDF and request to download this PDF, right? Let's move to the code part. All right. So I've already pasted this code. You can see over here, we are using request. Using request and PyPDF2. We are using bytes input and output and a load.env to just load the API keys for the Elastic environment, right? We are downloading the PDF. We are getting the pages based on each page number. We are just iterating and putting it to an array of pages. And we can start with printing it. All right. We do that. Okay. So you can see these are the pages. These are the documents of the actual PDF. We have downloaded this PDF and then created a variable that is pages, an array variable with different values, right? So now let's index this content to an Elasticsearch under index name my PDF index BM25. We do that. All right. So what we are doing over here is we are just using an Elasticsearch library from Python, a Python Elasticsearch library. We are implemented a client with an URL of an Elasticsearch and API key. We are using a bulk API to import this data to index this data to Elasticsearch. The index name is my PDF index BM25. The source, the data is the actual pages and the page number of each pages. We are iterating through a for loop, and first of all, we'll go and see this index actually exists or not. So this index does not exist currently. We'll run this command. Okay, my bad. Okay, let's run this. Okay, so let's reload. All right, you can see that the data has been indexed. All right, you can see that an index of my PDF index BM25 has been created with multiple documents. That is 16 documents and two fields. That is a text field, a keyword text field, and a page number, a long field. All right, let's use this index to do some context-based RAG searching. Use this background. Let's firstly select our indices. That is my playground indice. Okay, so once you have connected to the LLM, you can select your index and you can start asking question to the PDF. For example, something like what is layout parser and so on, right? So let's start with that. Okay, so you can see that it regenerated a question that is what is layout parser. Then it got context from our document source, different document based on the ranking. The score has been given to each document. And then this context has been given to the LLM, that is our OpenAI ChatGPT 4.0, and we got an answer. So what actually goes beside this, right? When we select this index, Playground determines the best available retrieval method. Since in our case, we are using something called BM25 keywords we're searching, it automatically generates a multi-match query to retrieve the document. You can see that over here, that the retrieval has created a query that is a multi-match query on a query on the field text, right? So if we have multiple field, you can choose which one to search, helping improve the relevance of the result, right? When you ask a question, the playground retrieves relevant document using selected method. It then provides those document as a context to LLM to ground its answer. By default, as you can see over here, we are using the field name text, which is used for the context, but you can use or edit it via the editing the context. You can always change your context field. Currently, we are Playground retrieves up to 3 default documents, but you can also change based on your requirement. It could be 5, it could be 10, based on your requirement on the A/B testing you are doing. All right. You can also ask follow-up questions, right? Follow-up question tied with the prior conversations. Playground rewrites these follow-up questions, use into a standalone one, allowing it a better document retrieval and ultimately more relevant result. Let's use how it is useful. How it is useful. All right. I have not given it what it is, but let's see if a playground is able to identify what it means over here, right? Let's see. Let's give it a second. All right. So you can see that the question was rewritten, right? So it was rewritten like how is layout parser useful in document image analysis based on what we have asked earlier. It just rewrote our question, gave us most relevant based on the context, it searched within the data and gave us an answer on how layout parser is useful, right? So you can see how this is tied up with the prior conversation, and you can always optimize the context. The document retrieved are passed as a context to the LLM. Playground picks a default field, but again, you can change it via the context editor. You can improve the retrieval. Of course, over here we are using BM25, a full text-based searching for the retrieving. But since the queries are often natural language questions, matching based on semantic meaning become critical, right? So semantic search and chunking comes over here. BM25 supports lexial matching, right? So it take to take it way further, we can use semantic search. Semantic sparse vector semantic search with ELSER is the answer for this. Elastic ELSER is a sparse embedding model that supports semantic search. ELSER is a 5 to 1 token limit, which means you will need to do smart chunking strategies to make it most of it. In future versions of Elasticsearch, Elastic will itself handle chunking automatically, but for now, we'll do chunking by paragraph, right? For chunking and ingesting the data, we will again use something called PyPDF and LangChain. It loads, splits the pages into passages, and then integrate well with the Elasticsearch, vector search, and re-ranking. Creating an ELSER interface endpoint is first thing we'll do. Before that, let's use REST API that calls, download, and deploy, and check if the model is actually running status. We will use these API calls via Kibana DevTools. You can see, let's firstly delete this model. All right. We are using the interface API of sparse embedding, and we are creating with an ID of my ELSER model. Let's create that. All right, it can take some time, but you can see that we have allocated different threads and num allocations, that is 1 and 1. You can see the status of this particular trained model. You can see this model has been started. Okay, so we are good. After this, what we'll do, we'll start the ELSA service in the ML node, and this might take a long, as you saw that, right? From this, the next step will be to set up an index and attach a pipeline that will handle the interface for us. To set up the ELSA pipeline and to embed the context, we'll use something called as ingest pipeline within Elasticsearch. What this ingest pipeline does, it just uses a processor, and we have used an interface processor and a model ID. We have given input field that is text and output field text embedding. This means that any input coming into text field will be given processed with a model that is my ELSER model, which we just embedded, and create a vector embedding based on that model. All right. After this, we will move on to put an index, right? We will set up an index which uses the embedded pipeline and will be ready to document our data and store our data, right? So let's put an index. You can see that we have two fields, that is text field and a text embedding field. Text field with a type text and embedding field with a type sparse vector. Sparse vector is a field which is used within Elasticsearch, a special field to store vector data within it. Right. And in setting, we have defined the default pipeline to use the above pipeline so that we embed our data, we convert our normal text data and enrich our text embedding data with some vector, right? So after doing this, we have index. Let's see if index has been created. All right, the index has been created with 0 documents. You can see over here. Now we will enrich the data. We will indice documents into the indices. So as you can see, we have used LangChain community, LangChain text splitter, and Elasticsearch modules of Python. We are just uh, creating chunks of 5 to 1, 512 size, and overlap of 256. Correct. And then using similar bulk API to ingest our data to a ELSER index with a field of contains and a page number. Right. Let's just quickly run this. Okay. All right. So this is what we can do. Okay. I see some errors. Index has not been created. Let's see. Let me just check if our model is ready. Okay, let's run the pipeline. Okay, let's this. We already have an index. Let's just recreate the index. There could be some problem because when the model has been recently created, there could be issue with the index as well. Let's recreate the index. Okay, now rerun this. Okay, so it's ingesting our data. Okay, let's refresh. Okay, let's give it some time to ingest all the data. So this over here, we are creating the vector embedding for each and every data, right? We are using ELSER model, the sparse encode embedding model of Elasticsearch, and the data will be ingested to this particular. Okay, now we can see, yeah, we can see that there is 33 document that has been ingested, and you can see three fields, that is text embedding, page number, and a text field, right? Text embedding is a sparse vector, a vector field within Elasticsearch to store this vector embedding. Page number, just a long field, and a text keyword field for just holding the text, actual text data. Right. Now we will use this semantic data and generate some ELSER based query, use semantic search to match with the meaning of our questions. Right. Let's do that. Use this particular index. All right. So this is when asking this question, we will now use semantic search query that is used to retrieve this document and that matches with the semantic meaning of the question. Let's ask some questions. How, what is your process? Let's start with that. Okay, so you can see that it gives context to the LLM and then created a proper output. Now let's move and see what's actually happened behind the scene, right? So you can see that there has been auto detected that we are going for a sparse vector query on the field text embedding. We have also given our model ID, that is my ELSER model, and our query. So you can see that Playground is smart enough to understand what we are doing. Over here, we are just doing a semantic search. You can always go for hybrid search. Okay, so just a click and you can see we are doing multi-match as well as a sparse vector query, a semantic search, and we are using something called as RRF. RRF is a reciprocal rank fusion algorithm to so that we can now retrieve data from both keyword and semantic search and re-rank them using this particular algorithm. Let's ask similar question with RRF. All right. All right. Now, this is hybrid search, which is very simple. By enabling just a text field, we have activated hybrid search for a better result and improve our answer. With LLM, to improve LLM answers with Playground, you can adjust the system prompt. You can trim and tune your retrieval strategies, compare across different chunking and embedding methods. You can see, you can just play around with prompt, you can update the context and so on. Based on anything and everything can be done over here. Soon, Playground will even suggest optimization tips for the retrieval strategies, right? And the optimizing the context, the better the performance. A great answers come from great context, right? So you can always experiment with chunking strategies, embedding model. And Elastic Elsewhere is great, but you can use different supported interface services. There is always a bonus for this, right? Optimizing context saves cost, boosts speed. Since tokens are less, so cost is less. Better chunking, fewer tokens, and a faster and cheap answer. So there is a great give and take when you optimize our context and save a lot of cost, right? The final step is just to integrate our final RAG application. We have done all A/B testing. We have played around with context interface, uh, prompt, and XYZ. Now, once you are happy with your experience, you can just export this setup and integrate with your app. Just with few click, you can just view your code. You can use Python Elasticsearch client with OpenAI, or you can always use LangChain Python OpenAI client. Right? You can just copy this code and use in your application. Just a quick view code option, which provides examples with both OpenAI and LangChain. But the underlying logic of Elasticsearch queries, system prompts, and LLM integration can be adapted to any of the stack. You can use any of the queries, you can update the prompt, you can use any of the LLMs. There are many ways to build a conversational search, right? And with so many options, it feels overwhelming. But Elastic Playgrounds make it easy building a GenAI powered applications and search applications. Simple, fast, intuitive, right? All while you have full control over the retrieval, context, and LLM while working best with performance. This was all from my. Now the floor is open for the questions.
So the floor is open for questions. We can all have your questions in the chat box right now, and we will take all your questions one by one. So Parivesh asks, how does Elastic RAG handle real-time document ingestion, and how quickly is newly ingested data available for search?
All right, I can answer that. So, if I talk about something with real-time ingestion of data, as I have explained, that we can use something called ingestion pipeline using different ingestion methods via APIs, connectors, something like pipelines using Logstash or Filebit. This pipeline can be enhanced using custom parsing, text chunking, and embedding generation, right? So you can always use something called ingestions with proper pipelines, and you can use this real-time data for proper indexing your data, enriching your data, and then using for the context and use it for the retrieval. So this process is a real near time. Typically, the document is available for retrieval within few seconds of being ingested, thanks to Elastic real-time indexing architecture.
Perfect. And we have another question which states, how will it handle diagrams and images in PDF? Will that require another embedding model?
Uh, I can take this one. So yes, it requires to have another embedding model. Because not every model is capable of creating embeddings. There are many models which are capable of creating embeddings for text one, because text one is easy, right? But images requires different set of attributes. So yeah, embedding is just converting the data into a numeric form. If you are able to convert it with your own algorithm, you can. So yeah, we need a different algorithm for handling images as compared to a text one. There are few other multi-model embeddings as well. So for example, ADA002, right? Is multi-model. So you can use text, and also you can use images as well for your embeddings.
Perfect. That's really good. Now we have another question that asks, what happens when the retrieved documents are noisy or conflicting? How does the model decide what to prioritize?
Okay. Whenever a document can be sometime noisy on conflicting, right? So this comes a proper chunking methodology. You can always chunk your data properly. You can play around with what your chunking strategy can be. Play around with how much context you want to give and how much you want to enable your LLM, ground your LLM, and you can always test and play around. So it's always best to do a proper A/B testing what works best for your use case and how you can properly uh, use the best how you can use RAG at its best.
Great. Thank you so much, Naman. Another question, can I use two models simultaneously to have both text and diagram embeddings?
Uh, yes, of course. This is what multi-model looks like, right? You can use two models simultaneously, both for text and diagrams. You can actually try to create separate indexes, right? You can have one index for text embedding, one for image embeddings, right? And you can query both separately and then merge the result as hybrid retrieval.
Great. Thank you. One more question that we do have is, how do you balance retrieval precision versus diversity to avoid overfitting responses in RAG systems?
Yeah, I can answer this. So, balancing a retrieval precision and diversity in RAG is really important and crucial to prevent anything, something like overfitting, that is overly narrow or repetitive answer, and ensure the response are relevant but rich with context, right? So, why this actually matters? Because too much precision can result in something called repetitive or overly specific responses, missing broader context. Also, too much diversity is also bad because it will give us irrelevant, noisy context retrieve, and LLM can get confused or hallucinate. So the goal is to retrieve just enough relevant data, but varied information so that LLM can generate grounded, insightful, and well-rounded answers. Right. So you can always balance this using proper tuning, using a proper score cutoff for relevance. You can always set number of documents. You can always work around with chunks, as I explained. Within context, within playground, you can always choose how many document you want to give to the LLM. You can always give it 5, you can 10, 20, whatever works for you. Play around with it. Strategy should be, we should give higher the context. The data should be more to promote diversity, but combined with mean score within our retrieval, so that the relevance should be high but the number of documents should be more. This works for best of most of the racks, but you is always recommended to play around and see what works best for the use case.
To simplify it, right, I think we can simply use a two-stage retrieval process.
Mhm.
The first one is that we can actually have a dense retrieval, which should be recall focus, and we can use vector similarity to pull, let's say, top k chunks. And then we can do a re-ranking, which should be a precision focus, right? So we can simply use a cross encoder for this. So yeah, this is how we can actually balance it.
Great. Thank you so much. I think another question that we have is, how scalable is Elastic RAG for organizations with large and dynamic data sets? I think this is a very important question because I think everyone nowadays is dealing with Elastic, is dealing with GenAI. So whether you're a startup or an enterprise, I think this works in all of them. So, Naman, Vishwajit, we'd love your view on this question.
All right, let me start. So Elastic RAG is highly scalable for organization because it is a distributed search engine, right? Elastic platform and Elastic approach is modular and a real-time data handling. So if we talk about Elastic is native to scalability, right? It can horizontally scale, indexing at scale. It can use something called ingest pipeline, log stash, and real-time indexing to ensure that data is searchable within few seconds. You can always use something called multi-tenant architecture that support multiple indices which are isolated across uh, different spaces and isolated access and performance, right? You can handle large amount of data within RAG using something called low code injection. You can just use connectors. You can just directly onboard dynamic sources like web pages, files, APIs, and so on. You can do real-time ingestion. You can use a vector indexing and BM25. You can do a proper hybrid search with semantic and keyword word searching. Play around with chunking and metadata. You can optimize your retrieval at scale without losing relevance. For example, uploading millions of legal documents or logs for hundreds of sources daily is feasible via automated pipeline, something like Logstash or connectors and a scalable indexing, right? Also, Elastic is really efficient vector at scale, vector search at scale. Elastic support ANN, that is approximate nearest neighbor, via dense vector field that use HNSW algorithm for fast and accurate vector search, right? It is optimized with higher dimensional vector that is nearly about 1536 dimensions, right? And large corpus with millions of chunks. So you can also segment vectors indices by topics, domains, and departments for better relevance and parallelizations, right? Also, when come to scale, security is one of the real concern of my clients, right? So rollback access control of Elasticsearch really help us to ensure that authorities have only authorized users can only access our data, right? With a query specific data set, field level or document levels security using Elasticsearch security and XPack, and a greater regulated environment, something specific to healthcare or finance. So if I have to conclude, Elastic RAG at scale is great for petabyte of data at indexing, real-time updates, millions of factors using ANN indexing, multiple source and dynamic data, secure and multi-tenant environment is supported. So anything Vishal, you might need to add?
Yeah, I mean, just to summarize, right? This is what Elastic is being made for, right? Handling scale. So yeah, I mean, it can handle any amount of data. It just depends upon your cluster size.
Great. So, next question that we have is what guardrails are in place to prevent RAG generated responses from misrepresenting retrieved source content?
I can actually go ahead about the guardrails. We have a thing called relevance filtering. So it only includes the chunk above a similarity threshold, right? So that we can have a faithful chunk selection in the retrieval step. Also, I mean, if there are any redundant or conflicting chunks from the same section, right? I mean, we can actually filter that. Apart from that, we also have this, I mean, metadata filtering as well. So we can exclude the, I mean, unverified, outdated sources using the metadata tags. Apart from doing re-ranking and, I mean, factual consistency. So yeah, this is what we can do for guardrails.
Perfect. And I think the last question for the day that we have is how do you tune ESRE to handle domain specific terminology such as in pharma or legal context?
All right, I can take this. So Elasticsearch Relevance Engine, that is ESRE, can handle some domain-specific terminologies, whether it be pharma, legal, healthcare, or finance. But this requires a careful curation of models, data, and a search behavior to ensure precision and contextual relevance, right? So as I said, you can always use different embedding models, right? You are not always restricted to use the Elasticsearch sparse encoder. You can always use something like LegalBart for legal embedding, FinBart for finance embedding. You can always look at Hugging Face to find your embedding model. Play around with it, see how you can swap out ELSER for external models. Use them. You can always use OpenAI embedding model like text embedding 3 small. You can always find endless embedding model at Cohere model. So you can always use this embedding model to store your vectors called something called sparse vectors or dense vector field and configure a proper relevant search engine using this particular index. right? If we talk about something really specific to domain specific chunking and indexing, you can always play around and do a proper semantic search chunking instead of native token or paragraph based searching. You can always set your chunking parameters and an overlap parameter, split based on section, case clause, or drugs based on your patient history or something like that. Something specific to a specific field. For pharma, you can use drug or patient data based chunking on each patient. Each patient should have their own chunks and so on, right? So relevant chunking can help. And a proper hybrid retrieval with dense and sparse. We can always don't rely on vector search, and in domain specific terms often have exact or a critical matches. For example, legal definition or drug names, right? So you can use the combination of keyword based searching and a dense vector similarity based off both world kind of thing, right? So using relevance engine, Elasticsearch Relevance Engine, you can do hybrid re-ranking. We can prioritize exact domain-based term matches and semantic closeness based on the embedding. Using this kind of strategies, using synonyms, using lots of strategies of chunking, retrieval, and a hybrid search, you can always work with relevancy and be really domain specific to help your use case.
Yes, the easiest way is to be able to make a custom analyzer, right? Like Naman, you said, we can normalize the acronyms, jargons, and alternative expression in that particular domain. So yeah, we can simply create this custom analyzer.
Perfect. Thank you so much, Vishwajit and Naman. This was a fantastic session. We really appreciate you taking out time to really break down how RAG and ESRE can elevate GenAI applications. And to everyone who joined us today, thank you so much. We are so happy that you have taken out a time from your busy schedule and have been such an engaged audience today. We hope that you are walking away with some valuable insights and a few ideas to explore in your own work. Before we sign off, just a few quick notes. I am going to drop the LinkedIn profiles of Vishwajit and Naman in the chat, so feel free to connect with them directly if you'd like to dive deeper or just continue the conversation. And also, this session has been recorded and it will be available on our YouTube, on our LinkedIn. We're going to be posting it, so you will be able to see it online as well. And if you're interested in collaborating with us on any future webinars or want to explore how Hyperflex can support your Elastic journey, whether it's consulting, managed services, or migration, please do reach out. We've added links to our contact page, LinkedIn, and email in the chat as well. Once again, thank you everybody for spending your time with us today. We look forward to staying connected and we hope to see you again in our next session. Until then, take care and have a great day. Thank you, everybody.